Hey, you guys. Sorry to be out again another day. Today's big adventure is going to an Iowa math conference. So, hanging out with fellow math nerds, including Mrs. Grodehouse and Mr. Edgerly. We're going to go present for one session on some silly stuff in math, and then we're going to go and watch the other folks and try and learn some other pranks to pull on you guys when we get back. So, it should be pretty fun. But now we got to pick up where we left off. And I know we went a little bit out of order the last time you guys went into rational functions. So that was just because that was familiar territory. And when I was gone, I thought, well, we're going to get there anyway, and we need to keep that in the backs of our minds. Rational functions, it involved long division. So if you weren't here on last Friday, you were looking at rational functions and you used long division to actually help find the end behavior. Remember, the quotient tells you what the graph looks like if you zoom out. And so by doing that, you're able to, that was something new. We found x and y intercepts on rational functions, just putting 0 in for x or for y and solving. So those are the things that happened then. And those videos, by the way, if you missed it or if you want to watch it again, they're all posted on Google Classroom. This today is dealing with what's in order where we left off. We're on page 5 of your note packet. And we're going to deal with multiplicity and polynomials and all their cool behavior. So think again, we're trying to look at the equation itself or the function itself and find things about the graph before we go in. We have access to the graph, even in these pictures here, but it still is misleading. So you got to be careful what you notice and use some of these tools to help you be a better grapher and notice things better. So first thing that's up on there is that multiplicity chunk. And I'll make sure my little writer is working. Here we go. I want to tell me a little piece of information, but multiplicity is a factor. How many times a factor occurs in a polynomial. So I'm going to show you some multiplicity things. If I zoom in real quick, and I'm going to do it just right on the sheet, that means x is a factor and it has a multiplicity of 2. It's basically, it's the same thing as the degree of the factor. So if you're looking at this, it's the degree of the factor is also known as the multiplicity of the factor. I'm going to make my font a lot smaller. There we go. And then there's this one here. Of course, this is 5. The degree 5 and degree 8 are easy to notice of those factors. And a factor is whatever is being multiplied to something else. So I'd say x plus 1 is the factor. X minus 7 is a factor. X minus 7 has a multiplicity of 8 because of the degree of that. Now, the one that tends to throw people off is x minus 3 has a multiplicity as well. X minus 3 has a multiplicity of 1. And I put it down below here because that's the first blank that's filled in. But x minus 3, sometimes you don't notice. And by the way, there's a typo in here. This x plus 5 doesn't make any sense. We don't have one of those. I think it's supposed to be x plus 1. There we go, because it matches. X plus 1 has a multiplicity of 5 up below or up above on the little polynomial that we have. Now, just to get it in another sense, now there's cool things about the multiplicity of the factor is it tells you a little bit about the graph. So its multiplicity, whether it's odd or even, so whether the degree of that factor is odd or even, tells us about what we're going to see in the graph at the root or the 0 of that function. So when we talk about an even multiplicity, so this one's the first little block here, even multiplicity, then a graph is blank to the x-axis at the corresponding 0. And it's the word I'm going to use, we've used before in a couple contexts, but it's tangent to. It's going to bounce off. So, and that's where I'm going to call this, I'm going to say it bounces at that 0. And that's my non-mathematical term, but it's the one that kind of helps me see what's taking place. So if I look at this graph and x minus 7 to the 8th right there, I'm going to give you a faux graph that goes with this. So here's my equation. Here's set x minus 7 means there's a 0 at 7, as in an x-intercept at 7. We've talked a little bit about how to find those. We just know if I were graphing this thing just by itself even, what you'd say is it's to the 8th power. This is an 8th degree, because remember you can distribute that power in there. Really, the degree of the function is if you have this 8 here, you want to look at putting that power on the x. If there's already a power there, you multiply, but you want to see that this would be a degree 8 polynomial, so we know that's even degree, and it's a positive degree 8 function, so we know that the arms face up because positive even. But now we have one more piece of information that's even better. The fact that x minus 7 is a factor to the 8th degree, it'll bounce at that 0. The 0 is 7, and I think you probably already picked up on that, because if you put 7 in for x, you're going to get out 0. So we know for a fact that it touches at x equals 7. And the way it touches, because the degree is even, is it bounces at that. Now, it can bounce from the bottom or the top. So this can be an upside down parabola-looking thing or one that's facing the other direction. So degree 8, by the way, I drew this sketch here as a pretty rough sketch of x minus 7 all to the 8th. That is really accurate because we know end behavior of all even degreed positive coefficient functions all end with their arms facing up like this. We have a root at 7, and we know it bounces. That's just a lot of information in just a glance. Okay, then we go to the next piece, multiplicity. Let's say it's odd. So we're going to change it up, go odd. Okay, and what happens is the graph passes through, and I'm going to use that probably because it's a little more accurate, pass through. Okay, so it's going to go through the graph, through the x-axis at the corresponding 0. Let's say it's x minus 3 to the first. That would count as an odd multiplicity. It's the degree of that factor. So for interest's sake, I'm actually going to put these two together this time. I'm going to call this y equals x minus 3. And I'm going to put x minus 7 to the 8th. Just so you know that together, if I had both of these, this were my polynomial, written out like that, what I'd know is that, hey, I got a 0 at 3, because if I put in 3 in this function, then I'm going to get 0 times some other number, and I get, 0. So 3 is a 0. If I put 7 in there, 7 times, or I get 0 in that right-hand factor, and 0 times anything is 0. So we know for a fact the output is 0 in those two locations. But what's really cool is we have a couple other things we can note. One is that the way the function touches at the 7, there is an even multiplicity. So I'm going to say right here, this one is going to have a bounce that we talked about in that last one. There's a bounce at 7. It's a 0, but it bounces there because of the even multiplicity. And then over here, I got a 0 at x equals 3, and it passes through. So what we're going to see at 3 is the graph will pass through. And I can put it in the calculator and all, but we know it's going to happen before we get there. And in fact, I know more, too. If I actually multiplied this out, like the day we did this last week, but if you just look at the degree of the x's alone, so this one right here is going to be x to the first, right? And then if I distribute the 8 over here, this is going to be x to the 8th. So in the end, if you have x to the first and x to the 8th, the degree of this is x to the 9th plus, I don't know. But you can just take the x's and their degrees within each factor, and if you multiply those together, you can add up their exponents. You just add up the degrees of the x's. You get x to the 9th. Do you remember x to the 9th is a positive, and it's positive because there's positive x's in each, has a particular end behavior. That positive odd behavior, remember, could have as much wiggle as you want in the middle, but the ends absolutely 100% finish left arm down and right arm up. Okay, so that's the known behavior. So what we see in our graph here is if I say x minus 3 to the first is one of my factors, and I say x minus 7 to the 8th is the other one, so you're seeing that down below. The odd one, the x minus 3 to the first, if I keep my behavior in mind, I know it ends and finishes a certain way around those roots. I'm 100% sure of that because it's a degree 9 polynomial. Then what I can do is from those end behaviors, I start at those arrows that I know so well, and when I get to the 3, I know what to do. My graph is going to pass through at 3 because it has odd multiplicity. And then when I come back around to catch the other 0 at 7, I know that it's going to bounce there because it had even multiplicity. So you take that, boom, and so it flies through. You can start with the end behavior by knowing the degree of the entire function without actually multiplying it out. Remember, you just take the x's and basically distribute the degree of that factor to each of the x's and then add their exponents all up. And when we get done, we have the end behavior to start with, check and check, and then from those end behaviors I was able to go up, hit each root in the appropriate fashion. And I hit 3 by passing through because it had odd multiplicity, and I bounced at 7 because it had even multiplicity. That sketch is not that sketchy. It's actually pretty accurate just because I know so much about it so far. Okay, we're going to keep rolling. So to get to that kind of accuracy in our graph, so now we're going to look at the graph together with this. We're going to take a function like this. It's a cubic. So right away your brain goes, oh, I know something about that one. It's a positive odd, so its left and right arms behave as such. And I'm over here on the graph if you can't see it. I know for a fact the left arm's down, the right arm's up. We already have the graph in front of us, so but it does confirm positive odd end behavior. Remember, the degree is the highest power of x. It's not necessarily on the far left. It often is, but it's the highest power of x that you find. Its coefficient is positive 1, so this is a positive odd end behavior. Great. But to get to all the zeros and root stuff, like, hey, what's going on here at this 0 or this x-intercept, or what's going on here? Where do they cross? I'm going to guess they cross at -4 and 0 just by looking at it. But sometimes you know how when you zoom in on the graph, you're just not sure what it does there. Like, does it pass through there? Maybe it just bounces just a little bit above at -4. Maybe that doesn't hit the way I think it does. Or is that exactly 0? What do I know about that? So to take the unknown out of it, we actually factor the polynomial. So we're going to take g of x right there, and we're going to take and factor it by pulling out greatest common factor. So old-fashioned, each of those has an x. They can be factored out of each of them. You get x squared plus 8, and then x plus 16 is what's left after factoring out the x. And then you look at what's left. The quadratic that's remaining has a, it's pretty easy to factor. Factors the 16 that add to 8. I'm thinking 4 and 4. Okay, so I'm going to factor it one more piece. So g of x ultimately factors to x. And this will become your standard. With the rational functions and with these polynomials, if you see something that's factorable, it's becoming pretty evident that you just want to go ahead and factor it if you can. Look for greatest common factor first, then look for quadratics you can factor. We want to make sure that skill is fresh, and if it's not, then maybe we should revisit that, and that's actually something on my agenda when I get back, is maybe check in with factoring again. But here it is, x plus 4 times x plus 4. To look at this, you could rewrite this just one more piece. If you take the same thing times itself, you all know that you can write that as x plus 4 quantities squared. Okay. And this brings us to where we just ended. The new information that we have is that, hey, if it's in factored form, I got some zeros. Now, x being out front by itself, that means a factor. One of my factors is x, and one of my zeros is whatever x makes that into. So, by the way, identify the multiplicity of each factor. So x is a factor. I'm going to put all this up here. And so it's x plus 4, okay, squared. This has a multiplicity of 1, because it is x to the first power. This factor over here has a multiplicity of 2, okay, for its degree. Ultimately, it's a cubic. What that multiplicity, remember, tells us is that we do have a 0 at 0. It's important that a 0 is what value of x makes this whole polynomial equal to 0. And so x equals 0 is one of our zeros or x-intercepts. -4 is one of our x-intercepts. Got it? So now when we were wondering where it crosses on that graph, if you had any doubt at all that it crossed -4, that doubt is erased. We know it's -4. If you're at all unsure if it crossed at 0, that doubt is erased. But notice in the graph, -4 bounces, and that's a product of, or at least it's a symptom of, the fact that the degree of the factor was even, multiplicity of 2. X plus 4, where that -4 0 came from, had an even degree, and it bounces. Your interaction of the graph with that intercept is a bounce, versus x to the first had a multiplicity of 1, an odd degree. The graph passes through at that location. Now, whether it bounces on the top or bottom is all about you starting. You start these sketches, you'll find out we want to get the end behavior first. Is it positive even, positive odd, negative even, negative odd? Where do the arms finish? You draw that first, and then from those end behavior arms, you get to the zeros and interact with them accordingly. So when I get to -4, it's getting even power, so you bounce there. And then you go down, you recover. Now, the part that's a little iffy is how high do you make your bounce? Like this, how high do I make this peak? Do I keep going? Do I drop down further? Do I make it taller? All that part is still a little bit of the sketchiness we don't know. We don't have enough information yet to talk about how far that loop is. So what I'm going to be assessing of you is that you just know that it bounces, and then you return in a smooth, curvy fashion, no sharp turns, to the next 0 and interact with that one accurately, which is passing through, because it had an odd degree factor. But how deep and how high you make those loops, the turning points, is not something I'm going to measure, or I'm going to assess of you. So here, case in point, let's go to it. Okay, so I'm going to go to a graph. This one's open. This is